There's a place in the universe where the rules of reality seem to bend, where the unimaginable becomes ordinary, and where the cosmos whispers secrets we're only beginning to decipher. This is the Leo cluster, a sprawling collection of galaxies so vast and mysterious that it defies everything we think we know about space. Picture this: thousands of galaxies, each with billions of stars, swirling together in a cosmic dance. Yet hidden within this spectacle are phenomena so strange, so utterly unexplained, that even the most brilliant minds can only stare in awe. What lurks in the shadows of this colossal structure? What forces are at work here that challenge the very foundations of astrophysics? The Leo cluster isn't just another patch of space. It's a frontier of the unknown, a realm where the ordinary laws of physics crumble under the weight of the inexplicable. From galaxies that move in impossible ways to ghostly energies that defy detection, this region is a treasure trove of cosmic enigmas. Some of these mysteries hint at forces we've yet to discover, while others seem to taunt us with questions that may never have answers. And that's what makes this journey so thrilling, because when we peer into the depths of the Leo cluster, we're not just observing the universe, we're confronting the limits of human understanding itself. Today, we're diving headfirst into 25 of the most baffling phenomena ever recorded in this corner of space. We'll unravel the stories behind vanishing stars, unexplained radio signals, and structures so massive they shouldn't exist. This isn't just a tour of cosmic oddities, it's an exploration of the edges of science, where every discovery raises new questions and every answer feels just out of reach. So buckle up, because what you're about to witness will challenge everything you thought you knew about the universe. The Leo cluster is waiting, and its secrets are more extraordinary than you could ever imagine. Right at the heart of the Leo cluster lies something so unsettling, it makes even seasoned astronomers pause. The Leo void. Imagine a bubble in space so vast you could fit thousands of galaxies inside it, except there's almost nothing there. This chasm stretches over 300 million light-years, a staggering emptiness that shouldn't exist according to everything we know about how the universe is structured. Most of space is woven together by galaxies, dust, and dark matter, forming intricate cosmic webs. But the Leo void, it's a gaping hole in that fabric, a place where the rules seem to have been rewritten. How does something like this even form? One theory points to dark energy, that mysterious force accelerating the universe's expansion. Could it have stretched this region thin, pushing matter away until almost nothing remained? Another idea suggests a cataclysmic collision, an ancient clash between the Leo void and another supervoid, like two cosmic ghosts passing through each other and leaving behind a near-perfect vacuum. But here's the problem: our models can't fully explain it. If voids this size are possible, then our understanding of how matter distributes itself across the cosmos might be missing something fundamental. What's even stranger is that the few galaxies trapped inside this void don't behave like they should. They're isolated, drifting in the emptiness like ships lost at sea, and some of them spin in ways that defy predictions. It's as if the void itself is warping the rules around them. Could there be hidden forces at work here, something beyond dark energy or gravity? Or is this a clue that our cosmic maps are incomplete, that there are phenomena shaping the universe we haven't even dreamed of yet? The Leo void isn't just an absence, it's a riddle, one that challenges us to rethink what we know about space, time, and the very structure of reality. Hovering at the edge of the Leo cluster, there's a galaxy that shouldn't look the way it does: NGC 3628, nicknamed the Phantom Galaxy for its eerie, stretched-out appearance. Viewed from Earth, it's a perfect edge-on spiral, a razor-thin disk of stars and dust that should be symmetrical, orderly, but something's wrong here. Its shape is distorted, warped like a vinyl record left too close to a flame, with vast plumes of stars' tidal tails stretching hundreds of thousands of light-years into the emptiness around it. These aren't just random debris, they're the scars of a cosmic collision, evidence that this galaxy was torn apart by a gravitational tug of war we can barely comprehend. What's truly baffling isn't just the violence of its past, it's what's missing at its heart. A galaxy this massive, this dynamic, should have a supermassive black hole anchoring it, a gravitational titan millions of times heavier than our Sun. Yet when astronomers peer into its core, they find nothing. No X-ray flares, no telltale heat signature, no swirling disk of doomed matter. It's as if the universe forgot to install the engine that should be powering this entire system. Where did it go? Could it have been flung into the void during the same ancient collision that warped the galaxy's disk? Or is something even stranger at work, a black hole that's cloaked itself, invisible even to our most advanced instruments? Then there's the mystery of its tidal tails. Most galaxies stretched by collisions show predictable patterns, debris scattered along predictable paths. But the phantom galaxy's tails are chaotic, twisting in ways that suggest multiple encounters or perhaps an unseen force still shaping them. Some researchers speculate dark matter may be sculpting these streams, an invisible hand guiding the chaos. Others wonder if we're seeing the fingerprints of a primordial black hole, a relic from the early universe drifting unseen through the wreckage. Whatever the answer, this ghostly galaxy refuses to follow the rules, challenging our assumptions about how galaxies live, die, and hide their darkest secrets. What makes NGC 3628 so mesmerizing isn't just the puzzles it presents, it's the quiet defiance in its existence. A galaxy this damaged should have faded into obscurity, its stars scattered, its structure dissolved. Instead, it burns bright, a cosmic phoenix clinging to its identity against all odds. And that's the real enigma, not just what happened to it, but how it survives. In the grand tapestry of the Leo cluster, the phantom galaxy stands as a reminder that the universe loves to break its own rules, and that some of its most haunting stories are still waiting to be told. Flung across the darkness like a cosmic necklace, the Leo ring is one of the most perplexing structures in the entire cluster. A perfect, shimmering loop of hydrogen gas nearly 650,000 light-years wide, encircling not one but two galaxies as if holding them in a celestial embrace. What makes this ring so extraordinary isn't just its sheer size or the fact that it exists at all, it's the way it defies every expectation we have about how such formations behave. Intergalactic gas clouds like this should be turbulent, chaotic nurseries where stars burst to life. Yet the Leo ring remains eerily quiet, its hydrogen untouched by the spark of creation. So how did this pristine ring form? The debate splits astronomers into two camps. The first argues it's a relic of the ancient universe, a leftover wisp of primordial gas that somehow survived untouched for billions of years, a fossil from the time before galaxies took shape. If true, it would be like stumbling upon a bubble of air from Earth's earliest atmosphere. Pristine, unaltered, a window into the cosmos's infancy. But the other camp paints a far more violent picture. A high-speed collision between two galaxies, a sideswipe so powerful it ripped gas from their outskirts and sent it spiraling outward, where it eventually settled into this hauntingly perfect ring. Simulations show such collisions can create similar structures, but none match the Leo ring's eerie symmetry or its strange refusal to form stars. And that's the real mystery here, the silence. Normally, a gas cloud this massive should be a fireworks show of star birth, gravity compressing hydrogen into glowing stellar furnaces. Yet the Leo ring lies dormant as if something is suppressing it. Could magnetic fields be weaving through the gas, stabilizing it against collapse? Or is the ring simply too diffuse, its particles too spread out to ignite? Some even speculate dark matter might be at play, an invisible scaffold keeping the structure rigid while stifling star formation. Whatever the cause, this ring challenges our understanding of how gas behaves in the cosmos, forcing us to reconsider the delicate balance between chaos and order in the universe's grand design. Perhaps the most haunting question isn't how the Leo ring formed, but what it's hiding. If it's truly a primordial relic, its untouched hydrogen could hold clues about the universe's chemical makeup before stars polluted it with heavier elements. But if it's the scar of a collision, why does it look so intentional? The galaxies at its center show no signs of recent trauma, their spiral arms undisturbed, as if the ring appeared without drama. It's a cosmic contradiction, a structure too perfect to be accidental, yet too strange to fully explain. In the grand puzzle of the Leo cluster, the Leo ring stands as a quiet enigma, a reminder that some of the universe's most elegant mysteries are the ones that refuse to fit into our neatest theories. Deep within the Leo cluster, a quasar performs a cosmic sleight of hand so strange it seems to defy the laws of physics itself. Designated QS OJ1148+5415, this brilliant beacon of light, a superheated disk of matter swirling around a supermassive black hole, should be fixed in place, a steady point in the sky. But it isn't. Over years of observation, astronomers have watched in disbelief as this quasar appears to wobble, dart, and even jump across space, changing position in ways that make no sense for an object billions of light years away. It's as if the universe itself is playing tricks on us. The most straightforward explanation points to gravitational lensing, the warping of light by massive objects between us and the quasar. Normally, this creates predictable distortions like cosmic funhouse mirrors bending light into arcs or rings. But here's the twist: no known foreground galaxy or dark matter cluster is massive enough to explain the quasar's erratic dance. Some researchers propose an unseen population of rogue black holes, drifting invisibly through intergalactic space, could be acting as microlenses, their gravity briefly magnifying and shifting the quasar's image. Imagine a swarm of invisible hands passing in front of a flashlight, each one tweaking the beam in unpredictable ways. Then there's the far more radical possibility: the quasar isn't being lensed at all. Instead, it might be part of a binary black hole system, two supermassive monsters locked in a tight orbit, churning spacetime itself into a turbulent whirlpool. As they spiral toward collision, their combined gravity could stretch and twist the quasar's light path, creating the illusion of movement. If true, we're witnessing the final moments before a collision so colossal, it would ripple the fabric of the universe with gravitational waves. But here's what keeps astronomers up at night. Neither theory fully explains the quasar's most bizarre jumps. Some positional shifts happen too fast, defying the timescales expected for black hole binaries or microlensing. Could this be evidence of something even stranger, an exotic form of matter warping light in ways we've never seen? Or are we glimpsing a flaw in our understanding of gravity itself? The dancing quasar doesn't just challenge our models, it taunts us, a cosmic riddle written in flickering light, daring us to unravel its secrets. What makes this phenomenon so captivating isn't just the mystery, it's the stakes. If microlensing is the culprit, it means the cosmos is littered with invisible black holes we've never detected. If it's a binary system, we're watching a once-in-an-epoch event unfold in real time. And if it's neither, then the Leo cluster is hiding physics we've yet to dream of. Every flicker, every shift in this quasar's path is a clue, a breadcrumb trail leading us deeper into the unknown. The Leo cluster is no stranger to cosmic violence, but nothing compares to the silent tempest raging through its heart, a hurricane of dark matter hurtling through space at speeds exceeding 1 million miles per hour. Unlike anything observed before, this invisible maelstrom cuts a chaotic path through galaxies, bending starlight and warping orbits in ways that leave astrophysicists reeling. We can't see it directly, but its gravitational fingerprint is unmistakable. Stars on the outskirts of cluster galaxies are being whipped into erratic paths, as if tugged by some unfathomable force. This isn't just a gentle current, it's a full-blown cosmic gale, and it's rewriting what we thought we knew about the universe's most elusive substance. Dark matter is supposed to move in predictable flows, pooling around galaxies like mist clinging to a valley. But this storm defies that logic. Its speed alone is staggering, far faster than any known galactic collision or merger should produce. Some researchers believe it might be the remnants of a dwarf galaxy torn apart eons ago, its dark matter scattered into this high-speed stream. Others think we're seeing something far stranger, a dark matter river, a primordial current left over from the universe's birth, one that's been rushing through the cosmos undetected until now. Whatever its origin, its behavior is the real shock. Instead of dispersing or slowing, the stream holds its shape with eerie precision, slicing through the cluster like a knife through water. The implications are profound. If dark matter can organize itself into such coherent, high-velocity structures, our models of how it shapes galaxies may be missing a critical piece. Current simulations suggest dark matter halos should be smooth and diffuse, not carved into these narrow, hyper-fast ribbons. Yet here it is, bending reality to its will. Some galaxies caught in its path show bizarre distortions, their outer stars dragged into elongated trails like cosmic breadcrumbs. Even more puzzling, the stream seems to avoid certain regions entirely, as if repelled by some unseen barrier. Could there be forces acting on dark matter we've yet to discover? Or is this a glimpse of dark matter's true, more complex nature? Not just a passive scaffold for galaxies, but an active, dynamic player in cosmic evolution. Perhaps the most unsettling question isn't about the storm itself, but what it carries. Dark matter is already a mystery, but this stream might be hiding something even weirder within it. A few astronomers speculate it could be laced with dark galaxies, clumps of dark matter dense enough to host stars, yet so devoid of light they've escaped detection. Others wonder if we're seeing hints of interactions between dark matter and an even more exotic particle, something beyond our current physics. One thing's certain, this hurricane isn't just passing through. It's a force of nature we've only just begun to measure, and its winds are blowing open the doors to a whole new frontier of cosmic discovery. Tucked away in the Leo cluster, there's a galaxy that whispers when it should scream, a seemingly ordinary spiral quietly radiating two enormous, ghostly lobes of radio waves that stretch millions of light years into the void. These aren't the blazing jets of an active supermassive black hole or the aftermath of a violent collision. Instead, they're faint, diffuse, and eerily symmetrical, like echoes lingering long after the sound has faded. What makes these radio lobes so perplexing isn't just their size or their delicacy, it's the fact that the galaxy at their center shows no signs of the chaos needed to create them. No swirling accretion disk, no outbursts of X-rays, not even a hint of the energetic fury we'd expect from an active galactic nucleus. It's as if the universe left the lights on in an empty room. So where did these colossal structures come from? One possibility is that we're witnessing the aftermath of a once ferocious black hole that's since gone dormant. Imagine a supermassive black hole feasting on surrounding gas in a frenzy, belching out twin jets of charged particles at nearly light speed. Over time, the feast ends, the jets shut off, but the lobes they created, like smoke rings from a long-extinguished candle, linger, slowly fading into the darkness. If true, this would be a rare glimpse into the retirement phase of a galactic engine, a quiet epilogue to a once violent story. But there's another, far stranger explanation. What if the energy fueling these lobes isn't coming from the galaxy at all? Some theorists suggest they could be the imprint of something invisible, a dark matter annihilation event where hypothetical particles collide and annihilate one another, releasing bursts of energy. Or perhaps they're evidence of a primordial black hole, one formed in the early universe, drifting unseen through the galaxy and stirring the interstellar medium like a spoon through honey. These theories push the boundaries of known physics, but the lobes' sheer scale and their host galaxy's silence make them hard to ignore. Even more baffling is their structure. Most radio lobes are messy, fractured by turbulence or distorted by intergalactic winds. These, though, are pristine, their edges sharp and symmetrical, as if carved by some unseen hand. Magnetic fields could be playing a role here, acting like cosmic molds to shape the particles into such clean forms. Or maybe we're seeing the result of a perfectly balanced outflow, a rare moment where opposing forces, gravity, pressure, and rotation, align to create something unnaturally perfect. The mystery deepens when we consider the lobe's light. Unlike the brilliant emissions from active galaxies, these glow softly at low frequencies, as if someone turned down the universe's volume. Radio telescopes strain to detect them, their signals barely distinguishable from the cosmic background noise. It's a paradox, structures so vast they could swallow galaxies whole, yet so faint they're almost ghosts. This has led some astronomers to wonder if the Leo cluster is hiding more of these spectral giants, their whispers drowned out by the cosmos's roar. What's at stake here isn't just solving a single puzzle, it's about rewriting the rules of galactic life cycles. If these lobes are relics of past Aegean activity, they could teach us how often black holes awaken and how long their echoes last. If they're signs of something more exotic, like dark matter or primordial black holes, they might crack open entirely new chapters in physics. Either way, these ghostly lobes are more than cosmic curiosities. They're a challenge, a reminder that even in the quietest corners of the universe, the most profound secrets often speak in whispers. In the vast expanse of the Leo cluster, a star once burned brightly enough to outshine entire galaxies, only to explode in a supernova so bizarre that it left astronomers scrambling for explanations. Designated PS14J1015+22540, this stellar detonation didn't fit neatly into any known category. Supernovae are supposed to follow predictable patterns. Type Ia bursts occur when white dwarfs steal too much mass from a companion, while Type Roman II explosions mark the violent collapse of massive stars. But this one, it straddled the line between both, a cosmic chameleon flickering with traits that should be mutually exclusive. At first glance, its light curve, the way its brightness evolved over time, matched a classic Type Ia, the kind used to measure cosmic distances. But when researchers analyzed its spectrum, the chemical fingerprints told a different story. Instead of the expected silicon and sulfur signatures of a white dwarf's demise, they found layers of hydrogen and helium hallmarks of a massive star's outer envelope, the calling card of a Type Roman II explosion. It was as if the universe had stitched together two different kinds of stellar death into a single, impossible event. Theories erupted. One camp argued for a freak stellar merger, a white dwarf colliding with a hydrogen-rich giant, their combined detonation blurring the lines between supernova types. Picture a thermonuclear bomb strapped to a gas giant, triggering a blast with identity crisis. Others proposed something even wilder, a pulsational pair instability, supernova, where a supermassive star teetering on the edge of collapse experiences violent, repeated eruptions before its final cataclysmic demise. Such events are predicted in theory but had never been observed until now. Then there's the rogue idea that this wasn't a supernova at all. A few researchers speculated it might be a tidal disruption event, a star shredded by a black hole, but the energy signature didn't quite match. Unless, of course, the black hole was spinning at near light speed, warping spacetime so severely that it mimicked a supernova's glow. The real enigma lies in the aftermath. Most supernovae leave behind neutron stars or black holes, but scans of the blast site revealed nothing. No compact remnant, no swirling debris disk, just an eerie quiet where a star once roared. Was the explosion so powerful it vaporized everything, or did the core collapse into something stranger, a theoretical object like a quark star or a dark matter mode too faint to detect? This supernova's refusal to fit the mold isn't just a curiosity, it's a crack in the foundation of stellar physics. If stars can explode in ways we've never imagined, what else might be lurking in the shadows of our cosmic models? The Leo cluster's impossible supernova isn't just a mystery. It's a beacon illuminating the gaps in our understanding and proving that even in death, stars can rewrite the rules of the universe. Amid the swirling galaxies of the Leo cluster, astronomers have stumbled upon something that shouldn't exist, a razor-thin, perfectly straight line etched into the fabric of spacetime itself. Stretching across nearly 500,000 light-years, this gravitational scar bends the light of background galaxies with surgical precision, as if the universe took a scalpel to reality. The leading theory, a cosmic string, a hypothetical relic from the universe's birth, when spacetime underwent violent phase transitions in the first split second after the Big Bang. Imagine the cracks that form in ice as it freezes, except here, the ice is reality, and the cracks carry more mass than entire galaxies packed into filaments thinner than a proton. If confirmed, this would be the first direct evidence of one of physics' most elusive predictions. Cosmic strings are thought to be defects in spacetime structure, regions where the fundamental fields of the universe got stuck during its rapid early expansion. Unlike black holes or neutron stars, they're not made of matter but of pure spacetime curvature, infinitely dense, infinitely thin, and under unimaginable tension. One string just a few miles long could outweigh Earth. The Leo cluster candidate fits the profile eerily well. Its gravitational lensing pattern shows no associated mass, no visible structure, just pure distortion along a single, unbroken line. The implications ripple far beyond astrophysics. Cosmic strings could be the ultimate laboratory for quantum gravity, offering clues to how Einstein's relativity marries with the quantum world. Some theories suggest these strings might vibrate at specific frequencies, producing gravitational waves detectable across the cosmos. Others propose they could serve as time machines. If two strings crossed or a single string formed a loop, the extreme spacetime curvature might create closed time-like curves, theoretical pathways to the past. Then there's the tantalizing possibility that cosmic strings could explain the universe's largest structures. Simulations show how their immense gravitational wakes might have herded matter into the galactic filaments we see today, like invisible hands sculpting the cosmic web. The Leo cluster's string candidate aligns suspiciously well with several nearby galaxy streams, hinting at this very role. Yet for all their theoretical promise, cosmic strings come with unsettling paradoxes. Their existence would mean spacetime isn't smooth at the smallest scales but frayed, like a fabric with loose threads. Worse still, if one were to pass through Earth, the event would be undetectable until suddenly, without warning, every atom along its path would be sliced cleanly apart by the sheer force of distorted spacetime. The hunt now turns to verification. If this is truly a cosmic string, it should produce double images of background galaxies arranged in telltale patterns, their light split by the string's gravitational knife edge. Future telescopes like the Vera Rubin Observatory may soon spot these signatures. Until then, the Leo cluster's phantom filament hovers between theory and revelation, a potential thread woven into the universe's deepest foundations waiting to be pulled. At the heart of one of the Leo cluster's most turbulent galaxies, a supermassive black hole is putting on a light show unlike anything astronomers have ever witnessed. Most black holes flicker predictably, their brightness waxing and waning as they consume matter in rhythmic bursts. But this one, dubbed the flickering giant, defies all expectations, flaring and dimming with no discernible pattern, its emissions spiking and plummeting like a malfunctioning cosmic strobe. One moment, it's a beacon visible across the universe. The next, it vanishes into near darkness as if something is flicking a switch at random. This isn't just unusual behavior, it's a direct challenge to our understanding of how black holes feed, grow, and interact with their surroundings. The first clue to this enigma lies in the accretion disk, the swirling maelstrom of superheated gas and dust that orbits the black hole before plummeting into oblivion. Normally, these disks glow steadily, their brightness tied to the rate of infalling matter. But the flickering giant's disk behaves more like a turbulent storm, with sections flaring up independently, as if chunks of it are being torn apart and reassembled on the fly. One theory suggests an unseen object, perhaps a second, smaller black hole, is plowing through the disk like a shark through water, stirring chaos in its wake. Simulations show such intruders could create shock waves that disrupt the disk's stability, leading to the erratic flickering we observe. Then there's the dark matter angle. Some researchers propose the black hole might be swimming through an unusually dense knot of dark matter, its gravitational pull yanking on the accretion disk in unpredictable ways. Imagine dragging a magnet through a pile of iron filings. The resulting mess wouldn't be smooth or symmetrical. If true, this could be our first glimpse of how dark matter interacts with black holes, a process that's been purely theoretical until now. But the most radical hypothesis, the flickering isn't caused by external forces at all. It might be an intrinsic property of the black hole itself, a sign that its event horizon is somehow unstable. Quantum mechanics suggests spacetime at the edge of a black hole should froth with particles popping in and out of existence. Could this quantum foam be bubbling up into macroscopic turbulence, causing the black hole's emissions to stutter? It's a long shot, but if proven, it would rewrite the rules of black hole thermodynamics. What makes this phenomenon so captivating isn't just the mystery, it's the implications. If accretion disks can be disrupted so easily, our models of how galaxies evolve might need revisiting. If dark matter is indeed tugging on the disk, we could be staring at a new way to map its invisible distribution. And if the flickering stems from quantum effects, we might finally have a bridge between relativity and quantum mechanics, two theories that have resisted unification for a century. The flickering giant isn't just a cosmic oddity. It's a laboratory at the edge of physics, one where the universe is running experiments we're only beginning to comprehend. For now, astronomers watch and wait, their telescopes locked onto this capricious behemoth. Every erratic pulse, every unexplained dimming is a clue, a piece of a puzzle that could reshape our understanding of the most extreme environments in existence. One thing's certain, in the Leo cluster, even the darkest objects refuse to stay silent. Somewhere in the depths of the Leo cluster, a galaxy simply vanished, not with a bang, not with a collision, just a quiet fading act, as if the cosmos had blinked and missed its exit. This was no majestic spiral or blazing quasar, but a humble dwarf galaxy, one of countless small stellar gatherings dotting the cluster. Yet its disappearance has left astronomers baffled. One day, telescopes saw it clearly, a faint smudge of stars orbiting the cluster's outskirts. The next, it was gone, replaced only by a wispy trail of stars stretched across space like the wake of a ship that had sailed into the night. The leading theory points to tidal disruption, the brutal gravitational forces that can shred a galaxy apart when it ventures too close to a more massive neighbor. Picture a snowball tossed into a river, slowly dissolving into the current. Here, the river might be the immense pull of the Leo cluster's central galaxies, their combined gravity acting like cosmic hands stretching the dwarf galaxy until its stars were torn free. Yet there's something odd about this stellar stream. Unlike other tidal debris, which tends to scatter chaotically, this one is eerily coherent, its stars aligned in a narrow ribbon that suggests a far gentler unraveling than pure destruction. Then there's the darker possibility. The dwarf galaxy didn't just get pulled apart, it fell into something. Dark matter substructures, invisible clumps lurking in the cluster, could have acted like hidden quicks and swallowing the galaxy whole while leaving only the faintest traces behind. These dark halos are predicted by simulations but have never been directly observed. If this is their handiwork, it would be the first evidence of their existence, a shadowy fingerprint on the cosmos. But the real puzzle lies in the timing. Dwarf galaxies are tough, often surviving for billions of years even in hostile environments. For one to vanish so abruptly suggests forces beyond the ordinary. Some researchers speculate the galaxy might have been exceptionally fragile, its stars barely held together by a wisp of dark matter, making it susceptible to even minor disturbances. Others wonder if we're seeing the aftermath of a rare event, a close encounter with an intermediate mass black hole, one massive enough to disrupt the galaxy but not so large as to leave obvious scars. The most haunting question isn't how the galaxy vanished, but what its ghostly remains can teach us. Stellar streams like this are cosmic archives, their shapes encoding the history of the forces that shaped them. By mapping the motions of these orphaned stars, astronomers might reconstruct the cluster's gravitational landscape in unprecedented detail, revealing hidden masses and unseen structures. In the grand tapestry of the Leo cluster, the vanishing dwarf galaxy is more than a mystery, it's a whisper from the darkness, a reminder that even the smallest players in the cosmos can leave the most profound questions in their wake. Nestled among the chaotic swirls of interstellar gas in the Leo cluster, something impossible rises from the cosmic haze, a nebula so geometrically precise it looks like it was etched by celestial architects. The hexagonal nebula defies every expectation of how gas behaves in space, its 6 razor-sharp sides stretching light years across, forming a structure more akin to a cosmic honeycomb than the usual billowing clouds of star-forming regions. Nebulae are supposed to be turbulent, asymmetrical, shaped by the chaotic forces of stellar winds and supernova shockwaves. Yet here, against all odds, nature, or perhaps something else, has crafted perfection. The debate over its origins splits the scientific community cleanly in two. On one side, physicists point to the power of plasma, arguing that under extreme magnetic fields, ionized gas can self-organize into geometric patterns. Earth's own polar auroras sometimes flicker with hexagonal shapes, a phenomenon called plasma crystals, where charged particles align under specific electromagnetic conditions. Could the same physics, scaled up to cosmic proportions, be at work here? Simulations show that if a dense neutron star or black hole at the nebula's heart spins just right, its magnetic field might sculpt surrounding gas into this unnatural symmetry, like a potter shaping clay on a wheel. But then there's the other camp, the one whispering about possibilities beyond known physics. The hexagonal nebula's angles are too precise, its edges too clean. Natural processes tend toward fractals and curves, not perfect 60-degree vertices. Some researchers cautiously float the idea of a Kardashev Type II artifact, a megastructure built by an advanced civilization to harness energy, its hexagonal form a byproduct of efficient engineering. While there's no direct evidence to support this, the nebula's eerie regularity raises uncomfortable questions. What if we're staring at the ruins of a project so vast it reshaped an entire region of space? Adding fuel to the mystery is the nebula's eerie silence. Most nebulae of this size hum with radio emissions, their atoms excited by nearby stars or embedded protostars. The hexagonal nebula, though, is acoustically dead, no telltale crackles of hydrogen, no rhythmic pulses from newborn stars. It's as if the structure exists in a vacuum, untouched by the usual cosmic chatter. Some suggest magnetic fields are locking the gas in stasis, freezing it in this unnatural state. Others wonder if something inside the nebula is actively suppressing star formation, a celestial off switch halting the birth of suns before they can ignite. Then there's the shadow play at its core. High-resolution infrared scans reveal a faint, grid-like pattern crisscrossing the nebula's interior lines of slightly denser gas intersecting at regular intervals. These could be shockwaves from long-dead stars frozen in time, or, as a handful of theorists propose, they might be scaffolding, the ghostly imprint of a structure that once was, or perhaps still is, hidden just beyond our perception. What makes the hexagonal nebula so unnerving isn't just its shape, but what it represents, a boundary. On one side, known physics straining to explain the impossible. On the other, the tantalizing void of the unexplained. Whether natural or artificial, this cosmic polygon challenges us to reconsider how matter organizes itself across the universe and whether we're truly alone in the quest to shape it. From the depths of the Leo cluster, a cosmic stopwatch is ticking gamma-ray bursts that stagger their arrival, defying the very notion of simultaneous events. Normally, when a star collapses or black holes merge, the resulting burst of gamma rays reaches us in a single, searing flash. But here, astronomers have clocked something bizarre. Twin bursts from the same cataclysm, arriving seconds apart, as if the universe itself hit pause between pulses. This isn't just a delay, it's a fingerprint of space-time twisting in ways we can scarcely imagine. The leading theory points to gravitational lensing, but not the kind we're used to. Instead of a massive galaxy bending light, some propose an invisible knot of space-time curvature, perhaps a primordial black hole or a wrinkle in the cosmic fabric, acting like a funhouse mirror for gamma rays. The first burst takes a direct path to Earth, while the second gets diverted on a slightly longer journey, creating that eerie split-second lag. It's as if the universe is echoing itself with the same scream arriving twice. Yet there's a problem. The energy signatures of these delayed bursts don't quite match. Lens distortion should preserve the light's properties, but these gamma rays show subtle differences in their spectral fingerprints, like two versions of the same song played in slightly different keys. This has led to wilder speculation. Could we be seeing evidence of extra dimensions? In string theory, higher dimensions could allow particles to leak between folds of reality, taking alternate routes through the cosmic landscape. One burst might travel through our familiar three dimensions, while its twin slips through a hidden fourth, emerging milliseconds later with a telltale energy shift. Then there's the quantum angle. Some models suggest spacetime at microscopic scales might be foamy, bubbling with virtual black holes that flicker in and out of existence. A gamma-ray photon could interact with this quantum foam, briefly splitting into two paths before recombining a phenomenon that would create precisely the kind of delayed double pulse we're observing. If true, it would be our first glimpse of quantum gravity in action, a bridge between Einstein's relativity and the subatomic world. The implications ripple far beyond astrophysics. If spacetime can stretch and split light so cleanly, our entire understanding of cosmic distances might need recalibrating. Worse yet, if the delays stem from unseen dimensions or quantum effects, we could be staring at the first cracks in our foundational models of reality. The Leo cluster's time-shifted gamma rays aren't just a curiosity. They're a stopwatch ticking down to a revolution in physics, one that might rewrite the rules of time itself. Among the bustling galaxies of the Leo cluster, one stands out for what isn't there, a spiral galaxy whose graceful arms should be glowing with stars and gas. Yet when astronomers point their telescopes toward it, they find only darkness. This celestial wraith, designated LSR 0945+2357, spins like any other spiral, its outer regions whirling at speeds that scream massive structure. But where there should be sweeping arcs of light, there's nothing. No stellar nurseries, no dust lanes, not even the faintest wisp of hydrogen. The gravitational pull is unmistakable, though something massive is shaping this galaxy's motion, something utterly invisible. The most obvious suspect, dark matter. We know it clumps around galaxies, forming halos that extend far beyond their visible edges, but this is different. Here, the missing mass isn't just a diffuse cloud, it's organized, sculpted into precise spiral patterns that mirror the structures we see in normal galaxies. It's as if someone took a template for spiral arms and swapped out the stars and gas for pure, unseen matter. Could dark matter, typically thought to be smooth and formless on small scales, somehow be capable of such intricate self-organization? Some simulations suggest it might, especially if dark particles interact weakly with each other, allowing them to clump in ways that ordinary matter can't. Then there's the magnetic hypothesis. Primordial magnetic fields, relics from the universe's infancy, might still thread through intergalactic space. If strong enough, these fields could channel and compress dark matter, shaping it into coherent arms like iron filings aligning to a magnet's pull. The idea isn't as far-fetched as it sounds. We've detected faint magnetic signatures in galaxy clusters before, though nothing on this scale. If true, the invisible arms of LSR 0945 plus 2357 might be the first visible, or rather invisible, evidence of magnetism's role in galactic architecture. But the real shock came when researchers looked closer. Deep radio observations revealed something even stranger. The galaxy's visible stars aren't just moving under the influence of these phantom arms, they're avoiding them. Like cars steering clear of invisible roadblocks, the stars' orbits bend around the empty spiral paths as if repelled by something. This isn't just gravity at work. It's as though the arms possess some other property, a force or field that deflects normal matter. Could we be looking at a new kind of dark matter interaction, one that doesn't just tug invisibly but actively pushes? Or is there an entirely unknown player in this cosmic dance? The implications stretch beyond one odd galaxy. If dark matter can form spiral arms, it might do so elsewhere, hidden in plain sight. Entire galaxies could be shaped by structures we've never seen, their true forms obscured by the limits of our instruments. Even more intriguing, if magnetic fields are involved, they might be the invisible hands guiding not just this galaxy, but the evolution of clusters across the universe. The Leo cluster's ghostly spiral isn't just a curiosity, it's a challenge, forcing us to confront how little we truly understand about the forces sculpting the cosmos. What makes this phenomenon so unsettling isn't the absence of light, but the presence of order in the darkness. Nature abhors chaos, and here, in the void where stars refuse to shine, something is still shaping the universe with precision we can't yet explain. It's a reminder that the cosmos doesn't need light to leave its mark sometimes. The most profound structures are the ones we'll never see. Deep within the Leo cluster, a cosmic metronome ticks with unnatural precision. And fast radio burst known as FRB 180925 that doesn't just explode once but repeats, firing off bursts of radio waves in a rhythm so exact it could pass for artificial. Most FRBs are one-off events, fleeting milliseconds of radio noise from distant galaxies, likely tied to cataclysms like colliding neutron stars or evaporating black holes. But this one, it returns. Every 131.8 seconds, like clockwork, it unleashes a pulse powerful enough to outshine entire galaxies, then falls silent, only to resurrect its signal again when the interval expires. It's not just repeating, it's rehearsed. The hunt for explanations splits scientists into warring camps. The naturalists point to magnetars, highly magnetized neutron stars that occasionally quake under the strain of their own intense fields. When these stars crack, their rigid crusts snap like planetary-scale tectonic plates, releasing energy that can ripple across the universe as FRBs. But for a magnetar to produce such a precise repeating signal, it would need to oscillate like a tuning fork, its entire structure vibrating in sync with some internal clockwork. Some models suggest this could happen if the star's solid crust floats atop a superfluid core, creating resonances that amplify certain frequencies. Imagine a bell struck underwater, its vibrations slowed and stretched into rhythmic, echoing pulses. Then there's the far more speculative camp, the one eyeing the possibility of intelligence. FRB 180925's regularity falls within what SETI researchers call the waterhole, a quiet band of the radio spectrum between hydrogen and hydroxyl wavelengths, where advanced civilizations might deliberately broadcast signals. The 131.8-second interval isn't just arbitrary, it's mathematically clean, a product of base 10 thinking that mirrors human timekeeping. Could this be a lighthouse, a beacon constructed to announce its builder's presence across the cosmic ocean? the idea isn't as far-fetched as it sounds. In the 1970s, astronomers designed the Arecibo message with similar intent, a deliberate radio pulse meant to announce Earth's existence to any listening civilizations. But here's where the mystery deepens. Recent observations caught the FRB doing something no alien transmitter should. Its polarization, the orientation of its radio waves, changes over time, twisting like a dial being turned. Natural cosmic magnetic fields could produce this effect, but only if the source is embedded in an environment of unimaginable turbulence, like the accretion disk of a supermassive black hole. Yet the signal's clockwork timing suggests stability, not chaos. It's a contradiction that defies easy explanation. Perhaps the most unsettling possibility is that we're witnessing something entirely new, a hybrid phenomenon straddling the line between known physics and the unexplored. Quantum vortices in neutron star superfluids could generate coherent pulses while their magnetic fields warp the emissions. Or maybe we're seeing the aftermath of a neutron star collapse that didn't quite finish, leaving behind a partially formed black hole ringing like a struck gong. Some theorists even float the idea of action stars, hypothetical dark matter objects that could decay in rhythmic bursts as they interact with magnetic fields. What makes FRB 180925 so compelling isn't just the unresolved debate, it's the realization that, for the first time, we might be watching the universe think in patterns we can almost but not quite comprehend. Whether natural or artificial, this signal is a cipher, a cosmic Morse code waiting to be cracked, and with every pulse it asks the same haunting question: are we listening closely enough? Somewhere in the chaos of the Leo cluster, a cosmic predator has broken free, a supermassive black hole, millions of times heavier than our Sun, hurtling through intergalactic space at speeds that defy reason. This isn't just a wandering giant, it's a runaway, ejected from its home galaxy with such force that it's now tearing through the void at nearly 5 million miles per hour, leaving a wake of distorted starlight in its path. Black holes this size are supposed to anchor galaxies, sitting motionless at their hearts like cosmic pit bosses. But this one, it's gone rogue, and the forces behind its escape are rewriting what we thought possible. The leading theory points to gravitational waves, ripples in spacetime itself. When two supermassive black holes merge, the resulting explosion of gravitational energy can kick the newly formed monster in one direction like a cosmic recoil. Picture two spinning tops colliding. The energy of their impact sends them flying apart. In this case, the kick comes not from physical contact, but from the asymmetry of the gravitational waves blasting outward during the merger. Simulations show these kicks can reach astonishing velocities, enough to fling even the most massive black holes clear of their host galaxies, the smoking gun. The rogue black hole's trajectory lines up eerily well with a nearby galaxy sporting a disrupted core, as if something colossal was recently ripped from its heart. But there's a twist. The recoil from gravitational waves alone shouldn't account for the black hole's current speed. It's moving too fast. This discrepancy has led some researchers to propose an even wilder scenario. Dark matter might have given it an extra push. If the black hole's home galaxy was embedded in a lopsided halo of dark matter, its gravity could have acted like a slingshot, accelerating the black hole beyond predicted limits as it escaped. Think of a pinball ricocheting off bumpers, each dark matter interaction adding another burst of speed. The problem: we've never observed dark matter interacting with black holes in this way until now, perhaps. What's most unsettling isn't the black hole's speed, but the trail it leaves behind. Unlike most rogue black holes which drift silently through space, this one is lighting up its path with shockwaves. As it plows through intergalactic gas at relativistic speeds, the friction heats the material to millions of degrees, creating a streak of X-rays visible across the cluster. It's a cosmic breadcrumb trail, one that glows brightest at the leading edge, where the black hole's gravity compresses gas into a glowing bow shock, like the wave cresting before a speeding ship. Then there's the question of its retinue. Supermassive black holes don't typically travel alone. They drag entire entourages of stars, gas, and smaller black holes along with them. Yet this fugitive seems startlingly isolated, as if it shed its celestial baggage during the violent ejection. The few stars still clinging to it orbit chaotically, their paths scrambled by the black hole's turbulent escape. Some show bizarre chemical signatures, hinting they were torn from the galaxy's innermost sanctum, where stellar nurseries brew elements under extreme conditions. The implications stretch far beyond one renegade object. If gravitational kicks can launch black holes this effectively, entire galaxies might lose their anchors over cosmic time, destabilizing their structures. And if dark matter plays a role in these ejections, we could be staring at a new way to map its hidden distribution by tracking the escape paths of these cosmic fugitives. The Leo cluster's rogue black hole isn't just a curiosity. It's a test case for the universe's most violent physics, proving that even the mightiest objects aren't immune to the cosmos's unpredictable whims. What makes this runaway truly mesmerizing is the possibility that it's not alone. Simulations suggest thousands of such rogue black holes could be lurking in the voids between galaxies, invisible except for the rare moments they interact with gas or stars. They're the universe's ghostly nomads, remnants of ancient collisions, carrying the scars of their violent pasts into the endless dark. And if one is blazing a trail this bright, how many more are out there, moving silently through the night? Hidden within the faint glow of the Leo cluster's cosmic microwave background, the ancient light left over from the Big Bang, there's a patch of sky that doesn't belong. A vast, eerie cold spot stretching over 1 billion light-years, where the temperature dips just a fraction lower than the surrounding radiation. At first glance, it might seem insignificant, a barely perceptible blemish on the universe's oldest photograph. But this anomaly defies every expectation, existing where our best cosmological models say it shouldn't, and the explanations for it, they're as wild as they are revolutionary. One hypothesis plunges us into the realm of parallel universes, a cosmic bruise left behind by a collision with another bubble of reality. Imagine the early universe as a frothing sea of space-time, where other universes might have formed alongside our own, each a separate bubble in an endless multiverse foam. If one of those bubbles brushed against ours long ago, the energy of that impact could have left a scar, a region where the cosmic microwave background was subtly drained of heat. It's an idea straight out of science fiction, yet some physicists argue the cold spot's size and temperature profile fit exactly what such a collision might look like. Then there's the counter-argument. What if the cold spot isn't evidence of a multiverse at all, but a wake-up call that our understanding of the cosmos is flawed? The standard model of cosmology rests on the assumption that the universe is broadly uniform, its matter and energy spread evenly across vast scales. But this cold spot challenges that assumption, suggesting there might be voids or structures so immense they distort the cosmic microwave background in ways we've never accounted for. Some researchers point to the possibility of a supervoid, an unfathomably large region of space emptier than expected lying between us and the cold spot. Light passing through such a void would lose energy, creating a subtle cooling effect. The catch, even the most massive voids we've discovered can't fully explain the cold spot's intensity. Perhaps the most tantalizing clue lies in the cold spot's strange polarization patterns. When scientists examined how the light here twists and turns, they found anomalies that don't match typical cosmic microwave background behavior. Some speculate this could be evidence of cosmic texture's exotic defects in spacetime itself, remnants from the universe's earliest moments when fundamental forces were still untangling. These textures, if they exist, would act like knots in the fabric of reality, distorting light and matter in their vicinity. But here's where the mystery deepens. If the cold spot truly is a sign of new physics, whether multiverses, supervoids, or spacetime defects, why haven't we found more like it? The cosmic microwave background is incredibly uniform, with fluctuations so minute they're measured in millionths of a degree. For this one region to stand out so starkly suggests something extraordinary happened here, something rare enough that its echoes remain unique in the observable universe. What makes the cold spot so compelling isn't just the battle between theories, it's the realization that a single anomaly, a faint chill in the afterglow of creation, could force us to rewrite the rules of reality. Whether it's a window into other universes or a flaw in our cosmic blueprints, this patch of sky reminds us that the universe still holds surprises too profound to ignore. And the answer, when it comes, might redefine not just the Leo cluster, but our place in the cosmos itself. In the heart of the Leo cluster, a star refuses to die no matter how many times it should. Astronomers have dubbed it the immortal star, a celestial anomaly that's endured not one, but multiple supernova-level eruptions, each powerful enough to tear an ordinary star apart. Most stars get one spectacular exit, a final blaze of glory before collapsing into a neutron star or black hole. But this one, it keeps coming back like a cosmic phoenix rising from its own ashes, defying every rule we have about stellar life cycles. The first clue to this enigma lies in its light curve, the pulse of its brightness over time. Normally, supernova flare brilliantly before fading into obscurity. The immortal star, though, follows a different script. Its eruptions come in waves, each flare nearly identical to the last, as if the star is stuck in a loop, endlessly replaying its own destruction. This isn't just strange, it's unprecedented. One theory suggests we might be looking at a Thorn-Zitkow object, a theoretical hybrid star first proposed in the 1970s. These exotic structures are thought to form when a neutron star gets swallowed by a red supergiant, nestling in its core like a ticking bomb. The neutron star's immense gravity would churn the supergiant's interior, creating bizarre nuclear reactions that could produce periodic eruptions instead of a single, catastrophic collapse. But here's the problem. Thorn-Zitkow objects should emit distinct chemical signatures, unusual isotopes like rubidium, lithium, and molybdenum forged in their turbulent cores. When astronomers analyzed the immortal star's spectrum, they found hints of these elements, but not in the quantities predicted. It's close enough to tantalize, yet just wrong enough to deepen the mystery. Some researchers argue this could mean we're seeing a new, undiscovered class of star altogether, one where the rules of stellar death are rewritten entirely. Then there's the timing. The eruptions occur with eerie regularity every few decades, as if the star is on a cosmic timer. This has led to wilder speculation. Could the immortal star be locked in orbit with another dense object, perhaps a black hole or a second neutron star? Each close pass could trigger a fresh eruption, stripping layers of material from the star while leaving its core intact to rebuild. Picture a vampire star, forever drained but never fully consumed, its life prolonged by the very thing that should destroy it. The implications ripple far beyond this one celestial oddity. If stars can cheat death like this, our models of stellar evolution might need a fundamental overhaul. Supernovae are cosmic recycling plants, scattering heavy elements across the universe to seed new stars and planets. But if some stars can erupt repeatedly, they might spread their ashes more gradually, altering how chemicals enrich their surroundings. And if Thorn-Zitkow objects are real, they could be hiding in plain sight, masquerading as ordinary giants while their neutron cores work invisible alchemy. What makes the immortal star so captivating isn't just its defiance of physics, it's the possibility that we're glimpsing a new chapter in stellar science. Whether it's a long-predicted hybrid or something entirely unknown, this cosmic survivor challenges us to rethink how stars live, die, and maybe even how they refuse to let go. In the grand tapestry of the Leo cluster, it stands as a beacon of the unknown, a reminder that the universe still has secrets written in fire and time. Stretching across the Leo cluster like a cosmic fire hose, a relativistic jet erupts from a distant quasar, only to perform a gravity-defying turn mid-flight. These jets are supposed to be nature's most powerful particle accelerators, blasting matter at nearly the speed of light in straight, unyielding lines. But this one, it kinks abruptly, bending at a right angle as if hitting an invisible wall. The laws of physics say such a sharp turn should be impossible without an unimaginable external force. Yet here it is, a paradox painted across the void, challenging our understanding of how energy behaves in the most extreme environments. The first clue lies in the jet's composition. These beams aren't just raw energy, they're plasma, superheated gas threaded with magnetic fields. Under normal conditions, those fields act like guide rails, keeping the jet tightly collimated. But something here has overpowered them. One theory points to an unseen galaxy lurking in the jet's path, its gravity warping the stream like a rock diverting a river. The problem: no visible galaxy sits at the bend's epicenter, unless, of course, it's cloaked in dark matter, its mass sculpting spacetime without a trace of light. Then there's the spacetime twist hypothesis. Einstein's equations allow for localized distortions, regions where gravity becomes so intense it twists the fabric of reality itself. If this quasar's central black hole is spinning at near light speed, its rotation could drag spacetime around it like a whirlpool, creating conditions where the jet's path appears to bend from our perspective. It's a phenomenon known as frame dragging, but never before observed on this scale. The jet might still be moving straight in its own warped reference frame, while we see a cosmic optical illusion. But the most tantalizing possibility involves magnetic fields of staggering strength. Some researchers propose the jet has plowed into a primordial magnetic filament, a relic from the early universe when spacetime crackled with energy. These filaments, if they exist, would be like cosmic power lines, their fields dense enough to wrestle even relativistic plasma into submission. The jet's bend could be a snapshot of that struggle, a moment where the universe's hidden infrastructure leaves its mark. What makes this phenomenon so unsettling isn't just the defiance of physics, it's the lingering question of cause and effect. Normally, jets shape their surroundings, carving bubbles in intergalactic gas. But here, the environment seems to be shaping the jet, a reversal that hints at forces far grander than we've accounted for. Whether it's dark matter, twisted spacetime, or relics of the Big Bang, one thing's clear: the Leo cluster's gravity-defying jet isn't just a curiosity. It's a signpost pointing toward the gaps in our cosmic maps and the unseen forces waiting to be discovered. Nestled in the quiet outskirts of the Leo cluster, a galaxy spins that looks hauntingly familiar until you peer closer. At first glance, it's a dead ringer for our own Milky Way. The same sweeping spiral arms, the same luminous central bulge, even the same satellite dwarf galaxies orbiting like loyal attendants. But when astronomers analyzed its starlight, they stumbled upon something that defies logic. The chemical fingerprints of this cosmic doppelganger are inverted, as if someone took the Milky Way's periodic table and flipped it inside out. Elements abundant in our galaxy are scarce here, and vice versa. Iron, magnesium, and silicon, cornerstones of rocky planets like Earth, exist only in trace amounts, while rare metals like europium and neodymium glitter in unusually high concentrations. It's not just a sibling galaxy, it's a mirror image, one that raises a spine-tingling question. Is this a freak coincidence, or could we be staring at a reflection from another universe? The simplest explanation points to cosmic variance, a quirk of star formation history. Galaxies evolve based on their initial conditions, and perhaps this one was born in a pocket of the early universe with an atypical mix of primordial gas. If its first generations of stars were unusually massive, they might have fused lighter elements into heavier ones more efficiently, skewing the galactic chemistry. But here's the catch: the Milky Way's twin doesn't just differ in composition. Its stars rotate in perfect synchrony with ours, their ages and distributions matching so precisely that statistical models put the odds of such similarity at less than 1 in a billion. It's as if two master chefs followed the same recipe with entirely different ingredients and somehow produced identical cakes. This has led to more radical theories. Some cosmologists suggest the galaxy might be a bubble universe artifact, a region where our cosmos momentarily brushed against a parallel reality during the inflationary epoch. In such a scenario, quantum fluctuations during the Big Bang could have created domains with inverted physical constants, including the ratios of fundamental forces governing nucleosynthesis. Over billions of years, these slight initial differences would snowball into the chemical disparities we observe today. The galaxy's structure remains identical because gravity behaves the same across universes, but the building blocks themselves tell a different story. Then there's the optical illusion hypothesis. What if we're not seeing another galaxy at all, but a gravitational mirage? Certain configurations of dark matter could, in theory, bend light in ways that duplicate and distort distant objects, creating a false twin with warped properties. The problem: no known lensing model can reproduce both the structural fidelity and the chemical inversion simultaneously. Either the match is real, or our understanding of spacetime's flexibility is woefully incomplete. Perhaps most unsettling is the philosophical weight this mirror galaxy carries. If it's truly a statistical anomaly, it forces us to confront how little we know about galactic diversity. But if it's evidence of a mirrored reality, the implications are staggering. Are there other inversions, regions where time flows backward, or where dark matter outnumbers visible matter 1,000-fold? The Leo cluster's Milky Way twin isn't just a scientific curiosity. It's a Rorschach test for cosmology, challenging us to question whether the universe we see is the only one that exists, or merely one reflection in an infinite hall of cosmic mirrors. Deep within the Leo cluster, two pulsars perform a cosmic duet so precise it defies everything we know about time and distance. Separated by thousands of light-years, these ultra-dense stellar corpses, designated Quasar J1034 plus 5701 and Quasar J1034 plus 5702, should spin independently, their rhythms dictated by local conditions and the slow bleed of rotational energy into space. Yet something impossible is happening. Their pulses lock into perfect synchrony, their beats aligning across the void as if connected by invisible strings. It's a phenomenon that shouldn't exist, a dance of celestial metronomes ticking in unison, despite the universe's insistence that no signal can travel faster than light. At first glance, the pulsar's synchronization seems to violate causality itself. Normally, any influence between them would need decades or centuries to bridge the gap, plenty of time for their spins to drift apart. Yet these two remain locked, their pulse rates mirroring each other with uncanny precision. One theory points to quantum entanglement, the same eerie phenomenon that links particles across vast distances, instantly correlating their properties no matter how far apart they are. But quantum effects aren't supposed to operate at macroscopic scales, let alone between objects as massive as city-sized neutron stars. If entanglement is at play here, it would mean the universe harbors connections far deeper and far stranger than we've ever imagined. Then there's the cosmic string hypothesis. Some theorists speculate these pulsars might be threaded onto a primordial defect in spacetime, a relic from the universe's birth that vibrates like a plucked guitar string, transmitting subtle gravitational nudges between them. If true, this would be our first glimpse of the universe's hidden scaffolding, a network of invisible filaments orchestrating cosmic motions in ways we're only beginning to perceive. But the most tantalizing possibility lies in the pulsar's shared environment. The Leo cluster is a gravitational maelstrom, its galaxies swimming in dense tides of dark matter and turbulent magnetic fields. Could these unseen forces be acting as a conduit, somehow forging a link between the pulsars? Simulations suggest extreme magnetic fields might temporarily couple neutron stars, aligning their spins through indirect interactions, a cosmic version of two tuning forks resonating across a room. What makes this phenomenon so unsettling isn't just the synchronization, it's the implications. If pulsars can influence each other instantaneously across such distances, our understanding of spacetime's rigidity might need revisiting. Or worse, what if this isn't influence at all? What if we're seeing evidence that these pulsars aren't truly separate, but projections of a single, deeper structure, a higher dimensional object whose true nature is hidden from our three-dimensional perspective? The entangled pulsars of the Leo cluster don't just challenge physics, they whisper of a universe far more interconnected than we've dared to dream. Tucked away in the Leo cluster, there's a gathering of stars that doesn't play by the rules, a shadowy congregation that emits no starlight, no twinkle, no visible glow. Instead, these enigmatic objects radiate only in the infrared, pulsing with heat but cloaked in darkness. This is the dark star cluster, a celestial anomaly where the usual glittering spectacle of a star cluster has been replaced by something far stranger. A swarm of objects that defy classification, lurking just beyond the reach of ordinary telescopes. At first glance, these shadow stars resemble failed suns, brown dwarfs too small to ignite hydrogen fusion, destined to smolder in obscurity, but the temperatures don't add up. Some of these objects blaze hotter than any brown dwarf should, emitting infrared signatures that suggest extreme, concentrated energy. One explanation points to degenerate matter stars, hypothetical objects that never quite became true stars. Imagine a stellar embryo that collapsed under its own gravity but stalled halfway, forming a dense, Earth-sized core of electron-degenerate matter, a kind of frozen star, too cool to shine visibly but radiating heat like a dying ember. These objects could exist in a limbo between planets and stars, packing the mass of Jupiter into a sphere no larger than Earth, their intense gravity trapping heat for billions of years. But there's a far more dramatic possibility. These infrared points of light might not be stars at all. They could be the retinue of an unseen supermassive black hole, a swarm of captured stars and gas clouds swirling in its gravitational grip. As these objects spiral toward oblivion, friction heats them to incandescence, turning them into infrared beacons before they vanish. It's a cosmic ballet where the dancers glow only in wavelengths invisible to our eyes, their final performances written in heat rather than light. What makes this cluster truly unsettling is its arrangement. Unlike typical star clusters which disperse randomly, these dark stars are densely packed, orbiting one another in tight, precise formations. Some researchers speculate they might be held together by dark matter's unseen hand, their motions dictated by an invisible scaffold we can't detect. Others wonder if we're seeing the remnants of a disrupted dwarf galaxy, its stars stripped of their outer layers by tidal forces, leaving behind only their scorched, smoldering cores. The implications ripple far beyond this shadowy gathering. If degenerate matter stars exist here, they could be far more common than we've realized, hidden throughout galaxies, overlooked because they don't shine. And if they're black hole hostages, their infrared glow could map the distribution of otherwise invisible intermediate mass black holes, lurking undetected in galactic halos. The dark star cluster isn't just a curiosity, it's a challenge to our understanding of what stars or star-like objects can even be. Perhaps the most tantalizing question isn't what these objects are, but what they're hiding. Infrared emissions can mask a multitude of secrets, from cloaked black holes to exotic states of matter. Whatever the truth, this cluster stands as a reminder that the universe's greatest spectacles aren't always the brightest. Sometimes the most profound mysteries simmer in the dark, waiting for the right eyes or the right wavelengths to uncover them. deep in the Leo cluster, a galaxy has become the stage for one of the universe's most mesmerizing illusions, light from a supernova that refuses to fade. Instead, it lingers, replaying its final explosion like a cosmic echo, with ghostly rings of light expanding outward years after the initial blast. This isn't just a visual spectacle, it's a time capsule, a delayed broadcast from a stellar death that challenges our most basic assumptions about how light traverses the cosmos. The phenomenon begins with a supernova, a star's cataclysmic end, that erupted over a decade ago, its light initially reaching Earth in a brilliant flash. But unlike typical supernova which fade into obscurity, this one left behind a series of concentric light rings, each appearing years apart. The reason? A vast, intricate labyrinth of cosmic dust surrounds the galaxy, acting like a hall of mirrors for the supernova's light. As the initial flash radiated outward, it illuminated successive layers of dust at different distances, each reflecting the light back to us with a delay. The result is an illusion of motion, a slow-motion replay of an event that should have been over in an instant, but here's where the mystery deepens. These echoes aren't just delayed, they're distorted, their colors subtly shifted, their shapes warped in ways that don't match our models of interstellar dust. Normally, dust scatters light predictably, like fog diffusing a street lamp's glow. Yet these echoes behave more like light passing through a shattered prism, suggesting the dust isn't uniformly distributed but arranged in strange, clumped filaments or even microscopic structures we've never observed before. Some researchers speculate this could be evidence of dust donuts, dense rings of particles shaped by magnetic fields or the gravitational influence of hidden objects. Others propose the dust might be laced with exotic materials, carbon chains, metallic crystals, or even frozen organic compounds that bend light in unconventional ways. The implications stretch far beyond this one supernova. If dust can sculpt light so dramatically, our entire understanding of cosmic distances might need recalibrating. Astronomers often use supernovae as standard candles to measure the universe's expansion, assuming their light travels unimpeded. But if dust is warping and delaying their signals, some of our most precise calculations could be off by margins we've never accounted for. Then there's the eerie possibility that we're seeing more than just dust. A few theorists suggest these echoes could be magnified by something invisible. Perhaps a network of primordial black holes or dark matter condensates warping spacetime itself. Imagine light not just reflecting off dust but bending around unseen gravitational lenses, creating a hall of mirrors on a cosmic scale. What makes this phenomenon so captivating isn't just the light show, it's the realization that even the emptiest corners of space aren't truly empty. They're filled with structures so subtle, so finely crafted, that they can stretch a single moment across years, turning a star's death into a symphony of echoes. And with each new ring of light, the Leo cluster reminds us that the universe's greatest stories aren't always told in a single flash. Sometimes they unfold in whispers, one reflection at a time. Among the countless stars drifting through the Leo cluster, a few defy the cosmic dance, entirely streaking across the void at speeds so blistering they're not just escaping their galaxies, they're punching free of the cluster's gravity altogether. These are the unbound hypervelocity stars, cosmic projectiles rocketing through space at a staggering fraction of light speed, their trajectories etched across the sky like scars from some ancient celestial battle. The mystery isn't just their speed, it's the sheer impossibility of their origins. What force in the universe could whip a star into such a frenzy that it abandons its galactic home forever? The leading suspect, a supermassive black hole's gravitational slingshot. Picture a binary star system, two stars orbiting one another, wandering too close to the monstrous black hole at a galaxy's core. The black hole's gravity tears the pair apart, capturing one star while flinging the other outward like a stone from a catapult. the ejected star rockets away with enough velocity to escape not just its galaxy, but the entire cluster's gravitational pull. This scenario fits neatly with hypervelocity stars observed elsewhere in the universe, but here's the catch. Some of the Leo cluster's runaway stars trace paths that don't lead back to any known black hole. Their trajectories seem random, their launch points lost to time. That's where the controversy ignites. A handful of theorists propose something far more radical. These stars might not have been flung by gravity at all, but pushed. Dark energy, the enigmatic force accelerating the universe's expansion, could theoretically create repulsive pockets where its influence outweighs gravity's pull. If a star drifted into one of these regions, it might experience a sudden, violent kick, like a surfer caught in a cosmic riptide. The idea remains speculative, but it would explain why some hypervelocity stars seem to originate from nowhere, their speeds exceeding even the most extreme black hole ejections. Yet the clues don't stop there. Spectroscopic analysis of these stars reveals another oddity. Many are unexpectedly young, their chemical composition suggesting they formed recently from gas clouds rich in heavy elements. This contradicts the traditional ejection model, which should favor older stars lingering near galactic centers. One explanation: they might be the survivors of cataclysmic stellar collisions, violent mergers that not only birthed new stars but turbocharged them with enough energy to punch free of their birthplaces. Imagine two stars smashing together like atomic billiard balls, the resulting fireball hurled into the void by the sheer force of the impact. What makes these stellar fugitives so mesmerizing isn't just their speed, it's where they're headed. Unshackled from the cluster, they'll drift forever through the intergalactic darkness, their light fading into the abyss. A few might eventually collide with other galaxies in the distant future, seeding them with foreign elements. Others could become rogue stars, destined to wander the cosmic backroads alone, their origins erased by time. The debate over their acceleration mechanisms isn't just academic, it cuts to the heart of how we understand the universe's most extreme forces. If black holes are the culprits, their ejection patterns could reveal hidden supermassive giants lurking unseen in the cluster's depths. If dark energy plays a role, it might hint at uneven distributions of this mysterious force, clumping in ways we've never detected. And if stellar collisions are to blame, it could mean hypervelocity stars are far more common than we've realized, their births tied to the universe's most violent reunions. In the end, these unbound stars are more than celestial speedsters, they're messengers. Each one carries a story etched in its velocity, its composition, its trajectory. And as they flee the Leo cluster, they challenge us to reconsider what we know about the forces that shape, and sometimes shatter, the bonds of gravity itself. Among the countless worlds drifting through the Leo cluster, one stands out not for what it is, but for what it isn't. Astronomers call it the phantom exoplanet, a world that appeared just long enough to taunt us with its existence before dissolving back into the void. It was first spotted through microlensing, a cosmic trick of the light where a foreground object's gravity bends and magnifies the light of a distant star. For a brief moment, the star's brightness flared in a telltale pattern, betraying the presence of an unseen planet passing in front of it. But when telescopes swung back to confirm the discovery, the planet was gone. No repeat signal, no residual gravitational pull, just silence where a world should have been. The leading explanation is as chilling as it is plausible. We might have witnessed a rogue black hole's fleeting shadow. Unlike stellar black holes formed from collapsed stars, these primordial relics could be as small as asteroids, yet just as massive as planets. Drifting unseen through the galaxy, their gravity would distort light identically to a planet during microlensing events, but with one critical difference. A planet's gravitational signature lingers as it orbits its star, while a black hole's would vanish once it moved on, leaving no trace behind. It's the ultimate cosmic sleight of hand, an invisible predator momentarily revealing itself by bending starlight, then slipping back into the dark. But there's another, equally dramatic possibility. The phantom exoplanet could have been exactly what it seemed, a real, tangible world, until something cataclysmic ripped it from its orbit mid-observation. Picture this, a planet cruising peacefully around its star when a passing star or black hole enters the system, its gravitational kick sending the planet careening into interstellar space. Microlensing events unfold over weeks or months, plenty of time for such an encounter to occur. By the time we turned our telescopes back, the planet might have already been hurled light years away, an orphaned world banished to the cold expanse between stars. What makes this phantom so enthralling isn't just its disappearance, it's the questions it leaves hanging. If it was a black hole, how many more of these invisible wanderers lurk in the cosmic shadows, undetectable except for the rare moments they betray themselves? Current estimates suggest there could be trillions, outnumbering stars in the Milky Way. And if it was an ejected planet, what violent encounter could have dislodged it so abruptly? Some simulations show that young, densely packed star systems can fling planets outward like cosmic pinballs, creating a population of rogue worlds untethered to any sun. The implications ripple far beyond a single missing planet. If rogue black holes are common, they could be the universe's dark scaffolding, shaping galactic evolution without ever revealing themselves. And if planets are routinely ejected from their homes, the number of wandering, lifeless worlds might dwarf those orbiting stars, a sobering thought for anyone dreaming of cosmic neighbors. The phantom exoplanet is more than a celestial ghost story. It's a reminder that the universe is full of fleeting wonders, here one moment and gone the next, leaving us to piece together their secrets from the echoes they leave behind. Deep in the heart of the Leo cluster, where galaxies swirl like cosmic storms and black holes churn the fabric of spacetime, something pulses in the darkness, a signal so strange it defies every label we've ever invented. Known only as the Leo Anomaly, this enigma broadcasts rhythmic bursts of energy that don't match any known celestial object. It's not the steady heartbeat of a pulsar, nor the furious glare of a quasar. It doesn't flicker like a magnetar or warp spacetime like a binary black hole. Whatever this is, it exists in a category of its own, a cosmic question mark blinking at us from the void. The first clue to its strangeness lies in its emission pattern. Most cosmic objects release energy in predictable ways defined by their spin, their magnetic fields, or the chaos of their surroundings. The Leo Anomaly, though, follows no discernible rhythm. Its pulses arrive in clusters, sometimes rapid fire like a machine gun, other times spaced apart by hours of silence, as if it's operating on logic we can't decipher. Even more perplexing is its frequency range. Unlike most astrophysical phenomena which dominate specific bands of the electromagnetic spectrum, this signal spills across multiple wavelengths, from radio waves to gamma rays, as if it's trying to speak in every language at once. Theories about its origin range from the plausible to the borderline fantastical. One camp argues for an undiscovered class of compact object, a theoretical quark nova remnant, where the core of a collapsed star doesn't form a neutron star or black hole, but instead condenses into a soup of free quarks, radiating energy in ways we've never observed. Others propose a supermassive neutron star, teetering on the brink of becoming a black hole, its immense density and magnetic fields creating oscillations that rip particles from the quantum vacuum itself. Then there's the darker possibility. The Leo Anomaly might not be an object at all, but an event. Some researchers speculate we're witnessing the aftermath of a collision between higher dimensional objects' brains or cosmic strings predicted by string theory, their energy bleeding into our universe as this eerie signal. If true, it could be our first glimpse of physics operating beyond the 4 dimensions we know, a crack in reality's facade letting slip something unimaginable. But perhaps the most unsettling aspect of the Leo Anomaly isn't its emissions, it's its location. It sits precisely at the gravitational center of the Leo cluster, where the pull of a supermassive black hole should dominate. Yet there's no visible black hole, no accretion disk, no telltale X-ray glow, just this signal pulsing from what appears to be empty space. Could it be a black hole cloaked by some unknown mechanism, its event horizon rendered invisible by extreme spin or exotic matter? Or is the anomaly itself the source of the cluster's gravity, a concentration of mass so exotic it doesn't obey the rules we've written for stars, black holes, or dark matter? As we close our journey through the Leo cluster's greatest mysteries, the anomaly stands as the ultimate reminder of how much we don't know. It's a cipher without a key, a phenomenon that refuses to fit into our cosmic taxonomy. Whether it's a new class of object, a flaw in our understanding of gravity, or something beyond current physics entirely, one thing is certain: the universe is stranger than we've dared to imagine. And somewhere in the darkness, the Leo anomaly keeps pulsing, waiting for us to listen closely enough to understand. From the ghostly perfection of the hexagonal nebula to the hypnotic synchronicity of those pulsars locked in an impossible dance, the Leo cluster doesn't just defy expectations, it shatters them. Each of these 25 phenomena forces us to confront the same humbling truth: the universe operates by rules we're only beginning to glimpse. Take the vanishing dwarf galaxy, a cosmic whisper erased from existence without a trace. Or the immortal star, a celestial phoenix that cheats death again and again. These aren't just quirks of nature, they're glaring holes in our understanding, screaming for new physics, new theories, perhaps even entirely new ways of seeing reality. Consider the implications. The Leo void challenges our models of cosmic structure, hinting at forces beyond dark energy. The phantom exoplanet suggests entire populations of invisible black holes or rogue worlds drifting unseen. And the Leo anomaly, it might be the most profound mystery of all, a signal without a source, a cosmic conductor orchestrating the cluster from the shadows. What binds these enigmas together isn't just their strangeness, but what they reveal about our place in the cosmos. We're not just observers of the universe, we're detectives piecing together a puzzle where half the pieces are missing, and the ones we have keep changing shape. This is why the Leo cluster matters. It's not just a collection of galaxies, it's a laboratory for the extremes, a place where the universe tests its own limits. The flickering giant's erratic pulses could rewrite black hole thermodynamics. The dancing quasar's gravitational sleight of hand might prove the existence of higher dimensions. Even the Milky Way's inverted twin forces us to ask, are we staring into a cosmic mirror, reflecting a reality where the rules are subtly or drastically different? Now it's your turn. What do you think powers these phenomena? Could dark matter be more complex than we've imagined? Are we seeing echoes of other universes, or simply the cracks in our own incomplete theories? Drop your wildest ideas in the comments. The best science starts with bold questions. And if you're hungry for more cosmic mysteries, hit subscribe. The universe is vast, and the Leo cluster is just the beginning. One thing's certain: out there in the darkness between the stars, the next great revelation is waiting. Will you be the one to uncover